Hello, welcome. Hi, I'm Loic. Let me go to the first slide. I want to introduce to you today to ultra wideband a little bit. I want to show you a little bit of my work, tell you a little bit how ultra wideband works, and show you a few use cases. So first, I'm Loic. I've been with NXP working on ultra wideband for the past 2 years. I'm an embedded system developer in the CTO organization, and I mostly work on mobile robotics and drones and rovers and stuff. So first, ultra wideband, or UWB. Let me show you one use case first. Keyless Go for cars. If you have a key fob where you can just sit in the car and it starts automatically, these usually work with RF signal strength. This could be hijacked by attackers to repeat the signal and do a relay attack, so that they take the signal of your key fob and hijack your car. Ultra wideband has a defense against that by the use of their ranging techniques. So with ultra wideband, you can measure the distance between two devices, and then measure the time of flight, and then measure the distance. And if the device sees that it's further away than the signal propagation should be, it of course doesn't unlock the car. So the best features for ultra wideband, the part that excites me the most is, of course, this time of flight measurement. We have an accuracy of ±10 centimeters, and we can also do angle measurements of ±3 degrees with multiple antennas, as you can see on the device on the rover here in the front. There we have multiple antennas with which we can PDOA, but let me get to that later. Another feature which is very important for ultra wideband is its robustness. It's very resistant to multipath and other interference from other signals due to its unique features. Its range is also quite good for as 100 meters in line of sight conditions. In the IEEE standard, it's innate that the security of this protocol is very good. We can cryptographically secure every part of the ranging message, so that attackers have it even harder to attack this communication technique. Also, it's real time. We can do update rates up to 1,000 times a second, which is awesome. So, what is ultra wideband actually? It's just a mnemonic for this technology. It stands for it has an ultra wide band. So we tell ultra wideband has a signal bandwidth of more than 500 megahertz, which is quite a lot more than other technologies like Wi-Fi or Bluetooth. This means also that it can only transmit its signal at a very low spectral density to not interfere with other signals. It also means that we can use a very short signal duration, so that the signal doesn't interfere in the time frame that much. Right now, the most important channels we have are the channels 5, 6, and 8, which cover the spectrum from 6.4 to 8 gigahertz. And they are mostly already standardized in Europe and in America, and other important countries also followed suit with the IEEE standard. When I talk about ultra wideband, I'm referring to impulse radio ultra wideband happening at 6.4 to 8.8 gigahertz. So I talked about the short signal duration. I'm showing here you one definite signal pulse. As you can see, the signal duration is here in nanoseconds. It's only 4 nanoseconds wide, which is very short in comparison to other signals like Wi-Fi. And here we have the time domain of the signal, which of course shows you that its bandwidth is more than 500 megahertz. This huge bandwidth and short signal improves its signal propagation, so that it can do direct path signals, of course. It can also be reflected off surfaces. but it also helps in signal propagation if you're not in a line of sight condition, because due to its nature, it can measure if the when the signal appears and when a reflection appears, and can discern between reflection and direct path. And this makes it much more robust in multipath environments. You can see here, if we have a line of sight condition, there the direct path is the strongest signal, and then reflections come in afterwards. In a non-line of sight condition, we have the direct path, which is not the strongest, but it's still received. And we have the first reflection, which is then the strongest, which is received a little bit afterwards. Our wideband modules can discern between these two and tell you in the which of the ones what the line of sight, and give a moniker if it's in a line of sight condition or not. So that covers how you can how ultra-wideband works, but how does arranging actually work? For that, there's four main techniques you can do. It's, of course, single-sided two-way ranging, where you send one message from the initiator device to the partner device, and then the partner device answers back in a certain time frame. And from these timestamps transmitted, you can calculate the time of flight by subtracting the reply time and the loop time from each other. That's time of flight, and we can get to accuracies of up to plus minus 20 centimeters. To improve on that, we can also do double-sided two-way ranging. So after we have one ranging round, we again send one signal to the partner device and receive one signal back. This improves the ranging technique by reducing the clock error on one device. So one clock is cancelled out by the equation, which you can see here. It's a little bit complicated, but it's not that hard. Yeah, in the end, it's the same again. You do it twice to improve the accuracy, and we can go down to plus minus 5 centimeters in ranging accuracy. The next technique, it's a little bit different. This time, we use multiple anchors to measure range to one partner device. This would be used in a room environment where you have anchors and a grid of ultra-wideband devices, and where you want to have your position in the room. So what you do is you have 4 anchors, each anywhere placed in the room. They send out messages, and your device reads these messages, and then from the difference in reception time, your device can measure and calculate how where it is in the room. The fourth thing I want to show you is the phase difference of arrival. It's PDOA. It can also say it's similar to TDOA, so time difference of arrival, but with phase difference of arrival, you measure the incoming angle of the ultra-wideband signal between two antennas, and from this phase angle, you can measure the angle of the received signal, which is one thing enabling the Follow Me rover. You can see there. It's if you have a signal from this device sent here, these two antennas measure the angle, and then this rover follows it. But I'll show you that later. So what's the point? You can do multiple measurements. What can we use that for? In the end, it's about a finer location. Other device, Bluetooth and Wi-Fi can mostly do accuracies of up to plus minus 50 centimeters. With only ultra-wideband, with only distance measurements, we can do accuracies of plus minus 10 centimeters. But if we include also the angle of arrival, we can have a very, very narrow position determination between only two devices. We can have plus minus 10 centimeters and plus minus 3 degrees of angle, which is an awesome improvement over existing ranging techniques. So what we are using it for is, of course, indoor navigation with the TDOA, either uplink or downlink TDOA. We can do item tracking with it, like the Apple AirTags, which are already enjoying quite a bit of use. Point and trigger control, so it's which is one point like the car access demo, where you can access the car with just walking up to it. So it's an improvement on the keyless go, where you have a more accurate and more detailed approach to it. It's could also be used for hands-free payment. So instead of waving your card in front of the reader, you just walk up to the reader, and it automatically pays for you, or you use your smartwatch, smartphone, whatever. Of course, also smart building access is very important. It's one thing that NXP is great at with the smart cards and NFC, which I'll also show you. Ultra Wideband brings you the best user experience to mobile access. It's accurate hands-free and access control in your pocket, and it's very, very, very secure. We can do corporate access, residential access. So if you have at home have your garage and you have your Ultra Wideband enabled car, it would be feasible that the car automatically opens the garage door for you to drive in and park in your garage and then close the door afterwards. The way we do it at the moment is that we use in combination Ultra Wideband and Bluetooth Low Energy. At first, you establish a Bluetooth Low Energy connection between the devices to exchange information, keys, ranging parameters, and then you use Ultra Wideband to measure the distance between the devices and enable the handover and open whatever you want to open. Next thing I want to talk to you is indoor navigation. This is mostly based on TDOA applications, but it could also be used with two-way double-sided ranging. The most interesting part is there that we can finally do the real indoor location like GPS, where you're in a mall or in a conference center like this one. You have your phone out and you download the map of the location, and then it shows you where you want to go, like to this conference room. It shows you a direct path, and it even shows you which direction you should go. I already spoke about it, but let me show you this use case again. Ultra Wideband Finder. This is the Apple AirTag use cases, or the Samsung smart tag use cases, where you have a little device which you put anywhere, like in your pocket, in a flight case, in your backpack, and with these you can locate this device in centimeter level accuracy up to 100 meters. Apple currently has, with their nearby interaction, has a little bit expanded that they utilize all of the iPhones to get the global position every time an AirTag sees another iPhone or whatever else Apple device, which is quite an awesome feature. I personally put an Apple AirTag into the flight case for that rover, and I could see that it was with me on the flight, was transported to the airport, and then was waiting outside for it to be loaded onto the luggage claim, which is quite awesome to have this security. Okay, yeah, my luggage is with me and not stuck somewhere I don't want it to be. Okay, let me talk to you about my work. It's in mobile robotics. First, we have the precision landing demo. There we use multiple anchors and an initiator on the drone to land on the rover. It can be moving too. We do that using multilateration with double-sided two-way ranging, and that way we can achieve accuracies of below 5 centimeters in the position, in the three-dimensional position. This is a fully autonomous landing of a drone on the rover, and as you can see, the drone starts fully autonomous. There's no handover. There's no operator that does any any inputs. We have just a safety operator in case something happens, and it lands autonomously on the rover. The next is this Follow Me rover. It's an indoor Follow Me, where you use ultra-wideband and the angle of arrival of these two devices to let the rover follow you. And it's using the Peaks 4 ecosystem to enable this use case. This is a test I did for this demo, where I had a path laid out on the ground with some tape, and I used this initiator to walk along this path. And on the left here, we have the representation of the measurements. We have in blue the measurements, and in green is the path it should look like as I taped it on the ground. As you can see, it follows pretty closely along all of the lines, except for here, which is where the ground slopes downwards a little bit. So the test environment wasn't perfect, but the measurements correlate very good with the actual marked track. And also I want to show you this video of the rover in action. This is from Embedded World earlier this year, and yeah. Oh, can you shut off the music? Yeah, we have the ultra-wideband module in front, and then we have the operator with the ultra-wideband initiator attached to his belt, and he can just walk, and the rover will follow him. But I will walk along all day with the rover, and you can ask me questions about it later. So, how can you get started? NXP has a wide ecosystem of ultra-wideband products. We have on the one hand automotive chips, the NCJ29D5, which is a range of 4 or range of 5 application of the ultra-wideband chip that's already being shipped in cars. For example, BMW and Volkswagen are implementing it into their key fobs and cars for keyless go applications. On the other hand, we have the mobile ultra-wideband chip, the Trimension SR100T, which is being shipped in Samsung phones for ultra-wideband applications. Then for IoT, that's probably most interesting for you guys, is we have the SR150, which is this chip. It's an ultra-wideband device which can have multiple antennas. So on here we have 2 antennas. On that chip we have 3 antennas with which you can do phase difference of arrival or whatever you want with multiple antennas. Then we also have the SR040, which is a low power, small tag-like chip that can be integrated into tags similar to the Apple AirTag and used exactly the same. And then we have the Trimension OL23D0, which is quite new, and I'll show you on the next slide. Our module partner, Synchronic IT, just released this chip. It's the world's first one-chip ultra-wideband solution. On here, we only have the ultra-wideband chip and 1 antenna, and Rabbi can show you later its application on the booth. Synchronic is offering a lot of software SDK kits and documentation on their website, and you can buy the chips from Future Electronics if you follow that QR code. One thing, smartphone integration, which we are also working on. Currently, Apple Nearby Interaction Kit and the Android Jetpack ultra-wideband library both enable you to communicate with your phone from an ultra-wideband device. These are in demo or alpha states. The Jetpack library is in alpha, and Apple is a little bit hush-hush with the Nearby Interaction Kit, but both are already working, and you can it enables you to use our products with Apple and Samsung smartphones. Another thing to mention is FIRA, which is the standardizing body of ultra-wideband, which concludes all ultra-wideband activities for us, and which enables most of the standardizing stuff that we are having. And that concludes my presentation. I hope you found it interesting, and we have time for some questions. Wait, did we have a microphone? Wait a second.
Is the certification required for this sort of application?
No, there's no certification required.
Okay.
Yes? No, not from FIRA.
No, but they do certification. So is it optional or?
What kind of certification do you mean?
Yeah, what certification is required really? Is there any, or like with
for legal for the channel width? I don't think there's any certification required. You just need to keep inside the allowed bandwidth power requirements, and yeah.
Okay. And another question: what's the practical range of this sort of application, like accurate positioning in the room? What size of room we're talking about?
So the
to
maximum
achieve that 3 centimeter accuracy.
The maximum range is 100 meters of these devices, and of course, if you use only phase difference of arrival, the position at 100 meters will be a lot wider because it's an angle measurement. At 2 meters, it's I think less than 5 centimeters in width. The position estimation at 100 meters would probably be like 1 or 2. Sorry, 1 or 2 meters. But for TDOA applications, it's the plus minus 10 centimeters position estimation for the whole 100 meters.
Thank you.
Yeah, no problem.
Hi. Yeah, you mentioned at one point fine ranging and also using it for the initial pairing and triggering an initial search. Does that essentially mean that the tag or similar can sit in a low battery, low power usage state for a long time until the fine ranging?
So the Apple AirTag has a lithium battery in it. The SL040 and the SL150 also have charging circuits for batteries and have battery protection systems. This device actually also has a port for a lithium battery. It can be used. Of course, you need to sporadically wake the device up with something. It depends on your use case how long the battery lasts, but usually for key fobs, car key fobs, it's up to 2 years with a battery. Yeah.
That's helpful. Thanks.
Yeah, no problem.
Just to follow up on my colleague's question, so if you want to produce a product that has one of those chips, so you're not required to get any certification for it?
I'm not the expert on that. You might like to ask Synchronic or my friends on the booth on that.
Okay. Right.
Yeah. Yeah.
So that's my second question. Do you need to get any sort of membership, like with Bluetooth? You need to get membership with the SIG to get the address or a service ID or something. Is there something similar to here?
The only thing would be maybe FIRA, but I'm not sure exactly.
Sure.
Sorry.
No problem.
I can just talk loudly. Do you know how the NXP chips compare with the DW3000?
It's mostly on accuracy. So I think the 1000 doesn't have a 2 antenna solution yet, or multiple antenna solution. It's mostly on accuracy and usability. Also with the new chip. Wait. This one, it's the first single chip auto wideband solution. It consumes a lot less power, and the documentation for it is much better.
Sorry, in the TDOA solution, how do you synchronize the anchors?
Well, at the start, you have mostly one master anchor, or probably you have one master anchor that sends out a package with a 2-way double-sided ranging, and every anchor answers and synchronizes the clock that way. And then you have that sometimes.
And the clocks are accurate enough to actually stay synchronized for a prolonged period.
Yeah. So you would have it like once every second or something like that, and then you can have 1,000 devices in a room all receiving the TDOA packages, and then calculating their position from that. Yeah. Another question?
One question about the ultra-wideband can penetrate the concrete wall?
Concrete, I'm not sure exactly. It definitely does lighter walls. For example, we have a application for ultra-wideband radar where you put that on a car windshield and it can penetrate the car seat. I think concrete depends on the size, but I'm not sure. I haven't tested concrete yet.
The Follow Me Robot application, will that eventually be able to be used on a smartphone too? You'll be able to have...
If I have the time, I would like to have that working with the phone, but at the moment I'm pretty busy with all kinds of stuff. I would love to implement that with the phone. It's planned for the future, yeah.
But if you don't have the phone yet, your little wrist device, it doesn't have to be that big, right? It could be
no, it doesn't. It doesn't. No, yeah, I had 3 months. That's part of my bachelor thesis, and I did what I had. I used what I had, and we have also these finder devices, so the SR040. That's just like this big, which could also be used. But I didn't have the time for the implementation.